Welcome back, everybody. We're about to talk about something that is incredibly complex and incredibly important in the VHDL design world, and that is synchronous design. Before we get started on the path of talking about synchronous design, we got to talk about some terminology first. So let's hit that terminology and see if we can understand what these two terms, the two most important terms, mean. We have the sequential system term, which basically refers to logic that will store or hold a value. So any logic that you design that is holding a value or storing a value is going to be sequential logic. So anything that has a flip-flop in it or a latch in it is going to be sequential logic. The other terminology that we need to, or term that we need to be familiar with, is the synchronous sequential system term. Now, it is a sequential system if it has storage. It is a synchronous sequential system if all of the storage elements are synced to the same clock. Okay, so everything changes at the same time. If you think of processors and microcontrollers, they typically run off a single clock source. That clock source is their synchronous clocking source, and that makes it a synchronous sequential system. Inside the processor, there's registers and other storage elements, and this clock makes sure everything kind of goes in step. Think in terms of like an orchestra. An orchestra maintains the pace of the music, okay, the tempo. It sets the pace, the tone. Everything is coordinated with the conductor, okay? Same thing with the clock. The clock is the conductor for the digital system, and it synchronizes all of the elements of the digital system so you have a coherent system to operate with. Let's take a look at an example here of some synchronous sequential system logic. Now, I've got two flip-flops in here to kind of give us an overview of what we're talking about, but the two flip-flops represent sequential storage, right? What makes them synchronous is that we have a common clock, the system clock, that runs into the clocking inputs for each of the flip-flops. So the system clock is synchronizing the operation of the system. The rest of the system basically consists of a, hold on there, presets, there we go. The basic system basically consists of, there we go, basically consists of some logic that we use between the flip-flops. So what we have here is we have some flip-flop for storage, and then those elements basically have their outputs feeding through some logic. It doesn't matter what the logic is for this example. It's and OR gates, it's all combinational. The important thing is these logic clouds, as I've drawn them here, basically have a propagation delay. Okay, so the logic clouds represent a propagation delay so that when a signal comes out, oh boy, I'm really having trouble with my tools today. So when a signal comes out, it goes through the logic and then it gets to the other D input a time later. Typical delays through flip-flop, well, there are no typical delays because it really does depend on the device, but you'll see sometimes 7-8 nanosecond delays for logic, and it depends not only on the delay through the logic elements, it also depends on the path delays when they're being transferred from one part of the silicon to the other part. So all of these play a part in driving the delays that you're seeing in your FPGA. So let's say that this logic here would generate, say, a 7 nanosecond delay. That means that when I clock it, I'm clocking both at the same time. This output right here can change, but that change won't be seen over here until 7 nanoseconds later. That means that I have to wait at least 7 nanoseconds before I can have my rising edge of my clock happen again, right? So I have to wait for that event to propagate, all that signal to propagate through before I can clock it again. Because if I clock it sooner than that, the signal may not have stabilized on the D input and it may pull in an incorrect value. The same goes for up here at the top. the logic path coming out of this flip-flop here feeds back through another logic cloud and feeds back into the first flip-flop. Now, when that happens, it could have a delay, say, of 8 nanoseconds. Because it's different logic, it's routed differently inside the device. So, that could actually have an impact on the frequency as well that we can clock at. So if this is a 7 nanosecond delay and the upward is an 8 nanosecond delay, we say this is the critical path delay because it is the worst case delay in our system. And so oftentimes in the output of some of your synthesis, you'll see critical path delay or worst case delay or something like that, longest path, different terms are used. But the idea is, what is the longest delay for logic to stabilize in my system before I can, and it determines what I can clock at, right? So in this case, even though if 7 nanoseconds later, the output from here to here reaches this, it takes 8 nanoseconds for this path to work. So we have to wait for all of the paths to propagate before we can clock again. And this directly impacts how fast we can clock our system. One of the things that's worth mentioning here is in a synchronous sequential system, the clock path is pretty important. If we're going to ensure that the clock is at the same time, we have to have special design considerations inside the FPGA that give us that ability. And so all FPGAs, CPLDs, and other devices really have dedicated low skew paths that are put in there by the designers to ensure that the clocks reach the register elements at precisely the same time. Now there's going to be plus or minus there, but it's very, very close to the same time. They work on path delays, they look at the routing structure of all the clocks, and they balance it out to make sure that there's no skew with one clock hitting a little bit sooner than the other clock on an element, causing some real havoc in your design, right? So we don't want that to happen. So this clock delays, these dedicated clock paths are important for having that happen. Technically, in design for sequential systems, you don't have to have just one clock. You don't have to have a single clock system. You can actually derive multiple clocks and run those multiple clocks in your system at the same time. It's an incredibly complex thing to do, and it's not very common. Okay, some more advanced designs might do it. It's useful for reducing power consumption in some parts of the chip, but the idea of a multi-clock system opens up a whole can of worms as far as how do you synchronize one set of the design with the other set of the design, and that's kind of beyond the scope of the course that we're doing. All we're basically worried about here, and most designs, to be honest with you, are basically focused around a single clock synchronous sequential system. And that's really what we're going to be talking about. But know that there are other options out there for more advanced VHDL stuff. Who knows? Maybe it'll be a more advanced class for us. All right, so let's review what we talked about before we start getting into some specifics of VHDL and synchronous design. And the important things to review here are that basically we need to ensure the stability of our design by making sure that the logic can fully propagate through the system before latching in new values. And this is the whole idea of determining the maximum clocking frequency. So like I said before, we want to make sure the logic has had time to stabilize before we run that through and clock it again. So the idea is, do you let the system stabilize to a final value, then you clock it again, and that ensures a repeatable operation. That gets to the next one here, which is basically allows for predictable sequencing through known states. And this means that you want to make sure that your clock paths are the same length. You don't want to have one flip-flop being triggered before another flip-flop. They need to be triggered pretty much at the same time within tolerance limits of the system. That's why they have these special clock paths put into chips. It varies from vendor to vendor and part to part as to whether how many clock paths you have, how they route the clock structure inside the device. But luckily, you really don't have to think about that most of the time unless you're trying to really push the limits in your design. Most of the time, you let the tool figure out how best to route it in that particular product. Remember, our focus is to create repeatable designs that can be used on multiple different vendor parts so that you're not tied to one particular vendor or another, and you basically have portable code. And so if you start worrying about an individual manufacturer's clock paths here and there, then you're really tying yourself to that one chip. Now that might be necessary if you're pushing the very limits of the chips, right? And you're trying to really squeak out something cutting edge. But for the most part, most designs aren't going to need to go into that kind of depth. All right, so we've seen what a synchronous sequential system is. We kind of understand the structure of how it works with storage elements, and then those storage elements feed information out to other logic, and that has to propagate through and feed to the inputs. But how do we do this in VHDL? Well, we do this through the use of processes. Now, a process is a tool, behavioral modeling is what we talked about before. It's a tool for creating sequential logic. It's not the only tool required for that, by the way, but it is the most common tool for that, or modeling style for that. And basically, to understand how VHDL creates a latch or knows to create a flip-flop, we have to understand how the process works slightly. The way it works is processes get triggered by events, okay? So we have a process sensitivity list like we talked about in our last video. If a signal changes on the sensitivity list, then that creates the process or triggers the process to execute and look at the results of that execution to see how it affects signals, right? So process gets triggered by a change, process executes, and then it finishes, it terminates. So when that happens, if it goes through and a signal that's an output of a process doesn't change, then the synthesis tool assumes you're wanting to store something. So remember what we talked about before. A process can always be drawn as a block, right? And a process can be drawn as a block with outputs. We'll put that as out 1. That can be out 1, and this could be out 2. So there's 2 outputs on this example, and then we can have a bunch of inputs, right? So processes can be drawn as a functional logic block with inputs and outputs. A process is responsible for a signal, an output signal, and is really the sole driver for that output signal, except in the case of tri-state logic, which we're not really going to address here. That's very specific to a certain type of logic. But for the most part, the output is controlled solely by that process. So the out 1 and out 2 are being controlled by the process. If the process gets triggered, executes, and doesn't modify out 1 or out 2 in this example, then the synthesis tool says, aha, that means I need to store this somewhere. There's a storage element that needs to hold a value. They're wanting me to hold this value, the state of this value, until the very end. And so that's how VHDL tells the synthesis tool to create storage elements. Okay, it's kind of strange and it's kind of unusual, and it's also kind of the reason why we have a lot of trouble with unwanted latch creation when we're doing combinational logic. If you remember when we were doing combinational logic, we said if you're going to do combinational logic, make sure that when the process executes, if you're doing it with a process, that you cover all the possible values. And even if not, selected signal assignment statements, forget the process. If you do a selected signal assignment statement and you don't use the keyword others, in the end, you're likely to create an unwanted latch. If your goal is combinational logic and having no storage flip-flops or latches, and you don't use the others phrase in a selected signal assignment statement, then you're likely to create an unwanted latch. In other words, a component in your design that will either be unnecessary or, at the worst case, cause erratic behavior in your design when it executes. So you want to really guard against that. And the other clause is a really great way to guard against that. So remember, when you're doing design in VHDL, it's important to decide, is that part of the design combinational or is that part of the design sequential? And you'll approach the design differently depending on which way you're going. So if you're doing a decoder or a multiplexer component in your design, that's combinational. So you're going to approach it in such a way that you ensure that all output signals, no matter what, get assigned a value if the process is triggered, okay? Or if the selected signal assignment statement is evaluated. So all of those need to be taken care of so that you ensure that you have combinational logic. If you're creating sequential logic, it's just the opposite. You need to make sure that when you're creating sequential logic that you have cycles that don't assign the value to it and then generates a flip-flop. That's actually quite easy to do when you see some of the examples. So if we keep those two things straight, it's going to make you a really good designer, and it's going to make it easier for you to handle sequential design using processes. Let's take a look at our first example. Now, I always like to start off with something really easy, and a D flip-flop is about as easy as it gets. Now, if you remember how D flip-flops work, they tend to have basically 3 inputs and 1 output, or 2 outputs, depending on what flip-flops you've used in the past. But the idea is you're going to have a clock input. The clock input actually triggers the storage of the value on D, and it transfers that value to Q. So remember, we're transferring a value from D to Q when the clock edge occurs in a flip-flop. Now, we also have shown a reset signal, and that's an important thing in our design, because in VHDL and any sequential design, you want to ensure that you have a state where you can reset the value to a known state. And this is incredibly important, especially in state machines, counters, and other things like that. Now, sometimes they're not necessary, but most of the time that's something you want to do. So in this class, we're going to be focused on ensuring that every logic that we create will have some way of resetting the logic to a known state. So let's see how we do it in this example here. Now, first off, I want you to notice that in our process, and I made a mistake, and we're going to have to fix that in the notes. But in our process, we have an input called reset, and we have an input called clock, and we have an input called D for the D flip-flop. Now, typically the naming conventions that we go by are lowercase for the signals, but in this case, since we're dealing with a fairly common element, I figured we would stick with the notation for simple D and Q outputs for a flip-flop. The reset input and the clock input should be part of the sensitivity list, because if either one of those values change, then we want to ensure that the flip-flop process gets executed, right? Because they have an immediate impact on the output. So if a clock comes in, that could have immediate impact on the output because it has the edge of the clock coming in, and we need to respond to that. If a reset comes in, we need to respond to that if it's an asynchronous reset. So we're showing an example here where we have an asynchronous reset. Now remember, there's 2 types of reset signals. There's asynchronous and synchronous. Asynchronous means that if it gets triggered by an active signal, it immediately changes. It doesn't depend on the clock at all. Whereas a synchronous reset is only occurring at the clock edge itself. So a synchronous reset only occurs on clock edges. It's synchronized with the clock. And we're going to see a lot of examples of synchronous inputs in our design, because when you're dealing with a synchronous sequential system, we're going to have a lot of synchronous inputs to deal with and work with as part of our design. So let's take a look at the sensitivity list. And as I mentioned before, I've got an error here that I will fix in the notes. This should be a reset signal, okay? So inside the process, it's important that we have all of the signals that need to change the output trigger the process. So we need to add the reset to the sensitivity list. So it would be clock, comma, reset as part of the sensitivity list for this particular process. Then when we get into the function, the first thing we check is the reset active? And if it is, we set 0 to Q. So we're going to clear the flip-flop. That's what the reset function does, is clears the flip-flop. If the reset is not active, then the only thing we want to respond to is going to be the clock edge, or the rising edge of the clock. So how do we do that? Well, the way you can do that is you can use the clock input, and you can look at some signal attributes that are part of the clock, of the signal. Now, all signals in VHDL have attributes, and we basically saw that in earlier when we were talking about signals, but let's put it to use here so we can see what's going on. Let's go and take a look at some of the things we're checking for in the next part of the design. We're first off checking for clock equal to 1. So when we check for clock equal to 1, we're making sure that the current state of the clock is high. Then we're checking to see if this was a clock event. And what that means is, did a change in this clock signal trigger the process? Is that what caused the process to execute? And every signal has that attribute that you can use and look at. And then the last thing was the last value of the clock equal to 0? So if the last value is 0, the current value is 1, and a change triggered this, that's a rising edge. And that's how we check for and ensure that we've checked for a rising edge in our system. And so this is the technique that you would use for checking for a rising edge. So we first off check for the reset value, then we use the else if to check for the rising edge. And if there is a rising edge, then we set the D value and write that out to Q. And that's what this assignment statement does right here. Okay, so that takes D and writes it out to Q, just like we would expect a D flip-flop to do. So this is an asynchronous reset because it doesn't need a clock to execute, okay? So it doesn't need a clock to execute. Notice that it satisfies the condition for sequential logic because there is a way for a signal to change and not trigger the process and cause it to say, hey, okay, I need to store. So if the process back that up. If I trigger the process and a signal doesn't change, that's what creates the latch. So what kind of signal could come in and do that? The easiest one to look at, lots of them will do that, but the easiest one to look at is what happens when we have a falling edge. So when the clock comes in, okay, and this is our clock, and it's a falling edge, will that trigger the process? And the short answer is yes. It's a signal in the sensitivity list. So if it changes, it triggers the process. So by triggering the process, that means we start executing. Is the reset active? Nope, reset's not active. It was the falling edge of the clock that triggered everything. Then, is this condition true? Is it a rising edge? And the answer is no, it's a falling edge. So what happens to the Q output? Nothing. Nothing happens. The Q output is left alone. So the process got triggered. The Q output didn't get changed or assigned at all, and therefore it creates a latch, or actually in this case creates a flip-flop to hold the value indefinitely in the design. So this is a sequential element. It creates a sequential element because of that. And that's pretty cool. So one of the things that, let's kind of review this. We talked about what makes it sequential. We talked about the sensitivity list and the fact that we need to change it. The thing that we didn't talk about yet is, what about D? D is an input. Shouldn't D be in the sensitivity list? Wouldn't that make sense to put D up here? And the answer is no. D doesn't belong there at all because D can change all day long and it's not going to have an effect on the output. The only way D influences the output is on the rising edge of the clock. If a rising edge of the clock happens, then D is transferred to Q, and that's the only time the value in D matters. If the clock is stable and doesn't do anything, as it stays low and there's no rising edge, then D can go all day long and will have no impact on the output whatsoever. And that is the reason D is not part of that. But remember what I said, this does need to have the reset though. So the reset should be in that list, and I left that off. I'll make sure to fix that in the notes. But that's an important piece of this. All right, so we've talked about an asynchronous reset. Let's take a look at a synchronous reset for a flip-flop. So we're going to go with the D flip-flop, and we're going to also talk again about a synchronous reset, the idea of being able to store a value, but then instead of an asynchronous, we clear it on the clock edge. And this is another alternative way to do initialization for all of your storage elements. We're also going to be introducing a new function to you that you're going to be super happy about, okay? Because if you remember, to test for the rising edge over here, we had to do this. Well, thankfully, the standard logic library, and specifically standard logic 1164 library, basically provides a rising edge function that we can use, and it takes care of all of that for us. In fact, that is pretty much the sole purpose of the function, is to check those signal attributes we just checked and to make sure it is indeed a rising edge. So in this particular case, instead of writing all that, we just call the rising edge function and make clock its argument. So now we check to see if the rising edge is by calling rising edge clock. Simple. And from now on, we'll be using that. There's no sense in going through writing the other stuff. This function was put in place to make it, number one, easier to type, and number two, much more readable. It reads a lot better when you say if rising edge of clock as opposed to this. Okay, so I think this cleans up the language quite a bit for us. Now, this is a synchronous reset, which means that it only resets on the clock edge. And so later on in the course, we'll talk about when to use synchronous and when to use asynchronous, or if you know, how to choose and which one has advantages and disadvantages, etc. So we'll address that later. But in this class, we'll be primarily focused on asynchronous resets. But that doesn't necessarily mean that has to be the way to do it. Some folks may prefer to do a synchronous reset. There are advantages and disadvantages for each one. Later in the course, we'll talk more specifically about the reset, but right now we're going to stick with asynchronous reset and run with that. So the synchronous reset, though, you need to understand how that works. Basically, we check for the rising edge first. And then remember, the synchronous means it is synchronized to the clock. So we check the rising edge first, and then we look to see if the reset value is set. So as soon as the clock edge has been detected, the first thing I do is I say, hey, is the reset signal active? If it is, I clear it. If it's not, then I check for the rising edge of the clock. Oops, that is completely wrong. Wow, I don't know how that got past my filters. This needs to just go away. In fact, this will be replaced with else. Goodness. So there is no, the test for rising edge is actually right here. Sorry about that. So if rising edge of clock, then, and we do reset, check for reset. And if it's not a reset, then it's going to be the normal operation of a clocked flip-flop, which would be transferring D to Q. So that would be a simple else statement there, and that would be the end of that particular declaration. Now, the last thing I want to talk about is the fact that when you're testing for rising edge, and let's focus on this because I don't want that to be I don't want that to be confusing. So notice how we're checking for rising edge of clock. Then inside that block, we check for the reset active, okay? So then we check for the reset active and the other stuff, right? Now there's a reason for that. You would never, and it's tempting, because if you're used to writing in other languages that aren't hardware focused, then you might say, well, why don't I just say if rising edge is clock and the reset's active, all in one line, right? Wouldn't that make it cleaner? Just say if rising edge and the reset active. No, actually that is an invalid specification. You can't check for an edge at the same time you check for a state. That makes no sense from a hardware standpoint. So here's the easy rule of thumb. Whenever you check for a rising edge, do it alone. Never check for other things. Never compound the statement and try to say is rising edge and this and that in a single expression. Always do rising edge by itself without anything else, and you are going to be great. You start playing around with these other things and you're going to create lots of problems for yourself. So just remember that one rule of thumb and you should be fine. Never combine rising edge test with any other logic. All right, so let's take a look at one more example. And this example is going to be the synchronous load and clear register. So thus far we've talked about a single bit. Now we're going to talk about a full register, right? So we've talked about a single bit. Now let's expand that to a full register. So let's pretend that we have some register, and it really doesn't even matter what size it is. And the register, well, let's go ahead and specify a size over here. Let's take a look, and let's call out this register. Let's say that it has a settings input, and let's say that the settings input is here. We're going to zoom in on this so we can all see it together. Setting input is, I don't know, 32 bits. Okay, it really doesn't matter. And then we have a value output that's also 32 bits. So the idea is you have a 32-bit register. The 32-bit register holds a 32-bit number or value inside. And all the rest of these signals are used as a way to store the information. You can actively load the signal by activating the synchronous load. You can clear by activating the synchronous clear. Otherwise, it does nothing. Okay, so this is a register that requires control signals in order to operate. So it won't do anything. It'll just hold the value unless you activate load, which tells it to load a value, or you activate clear, which tells it to clear the value to all zeros. And that's how this will work. So let's pretend we have a 32-bit vector called settings and a 30-bit vector called value. Okay, so settings and value are both 32 bits. Now let's take a look at this and see how it would work. It's specified exactly the same, which is really nice, right? So we don't have to learn anything new in specifications. We check the rising edge of the clock first by itself. Then we jump in here and we check to see if the clear is active, because we're giving clear precedence here. We're giving it a higher priority by testing it first. I could have tested the other one first to give it higher priority, but typically for clear functions, you would do that. If it is clear, then we're going to execute this line, which writes all zeros to the register here, to the 32-bit value. If it's not, then it checks to see if the load was active. If the load's active, then it basically takes the value from settings and assigns it to the value. It takes the number from settings or the input from settings and writes it out to the value output. Okay, so that's pretty cool, right? So now we've got this two control signals that control. What if neither one of them are active? Well, nothing happens. It just holds the value. There is no extra event or happening here. Nothing happens. So that's basically how this thing works. One last thing I want to mention here is this alternative way to write zeros to a vector. Now this is an important thing to be able to do, but what happens is by specifying it this way, the size of the vector doesn't matter. It could be 32 bits, 64 bits, 16 bits, 8 bits, it doesn't matter. It takes all signals, when you see this others, and assigns a 0 to each and every one in that vector. So each and every element in that vector gets assigned a 0 with this particular notation. So this is a way to clear a vector which you don't know the size for, or you really don't want to specify the size for. Later on in the term, we'll get into generic components, which is going to make it really neat for you to create these universal components that can be any size. And this kind of initialization is going to be important for that. Okay, so basically in this particular design, the clock here is only responsible for synchronization. It has absolutely nothing to do with the rest of the design. You have to either initiate a load or you initiate a clear by activating those control signals. And if they don't get activated, it holds the old value and keeps it there. All right, so that's it for today. We just kind of dove into the synchronous sequential systems and learned a little bit about what that means. Next time, we're going to talk more about specific synchronous types of devices. And so we'll see some examples of different synchronous elements in our designs. Thanks for watching, and we'll see you next time.